So hello there and welcome to another tutorial. My name is Tanmay and today we're going to be going through an absolutely fascinating topic. We're going to be talking about the AlphaGo series of algorithms. Now, I'm absolutely certain that you have seen of or heard about this new AlphaGo technology. AlphaGo is the very first system ever, very first computer system that has ever defeated a Go world champion, a human player. And this is absolutely exceptional because, well, if you take a look at other complex games, for example, chess, they have a very large state space. That means there are tons of possible moves, but still many decades ago, IBM was able to create Deep Blue, the first computer to ever beat a human chess champion. And that was incredibly impressive, but the way that works is fundamentally brute force. You're looking through almost every possible future move in order to determine your probability of losing or winning or tying the game, and based off of that, choosing the moves that give you the highest probability of winning. Now, the issue with that is that, first of all, you have to have human-crafted heuristics to guide your search. Because while chess is relatively a lot smaller than Go, and we'll get to that in just a moment, it's still really large. And that means brute forcing every single possible move is simply impossible. You can't do it. And so you somehow have to create these heuristics to tell you, this branch is so exceedingly unlikely on my opponent's part that I might as well not even consider it. And same thing for your own player. And so somehow you have to create human-crafted heuristics, and these take years to build good ones. And you need to use brute force, lots of compute, to really take a look into the future and forcefully figure out what's going to be happening. But then, AlphaGo completely changes the way games like this are played. And it has to, in a way, because in Go, there are more possible moves, there are more possible individual states and playouts of a game than there are atoms in the observable universe. And so no computer system can really model that entire state space of Go. The techniques that we've used for essentially every other game won't hold up for the game of Go. Now, there have been a few techniques applied to try and play the game of Go in the past. Almost all of them have been based on something called Monte Carlo tree search. Now, Monte Carlo and Las Vegas algorithms are a certain class of algorithms that work in a fundamentally random manner. That means they're not deterministic, they're stochastic. And so, for example, while a Las Vegas algorithm may not always necessarily give you the correct or always even give you a result, a Monte Carlo algorithm is guaranteed to give you at least some result. So that's the difference between the two. And Monte Carlo tree search specifically is able to make use of that random factor in order to take a look into the future, but not too far into the future and not through too many states. So what exactly does that mean? Well, let's take a look at what Monte Carlo tree search really is, and then we'll get into this whole AlphaGo, AlphaZero thing, and specifically the example that I want to show you today. So let's take a look, shall we? Now, AlphaZero or AlphaGo are fundamentally reliant not only on deep learning and machine learning technology, but they're also reliant on this other kind of technology, Monte Carlo tree search. So the way this works is ensembling new techniques and old techniques together. So let's take a look at how exactly that technology works. Now, let's just say we have some sort of Go board state, and it's going to be represented with this dot. Now, the thing is, there are tons of possible moves from this dot. So one thing that you could do is something called a Monte Carlo evaluation, where, for example, you say, all right, I'm going to take a look at, let's just say, every single possible move from here on out, and I'm going to modify the state so that I take all of those actions, and then I'm going to run a series of completely random games from that point onwards. Okay, and so on and so forth. You're just going to run completely random games until the game ends from that board state onwards. That's it. Now, I know it doesn't seem like this would do anything, but if you run enough random games, then what ends up happening is the states that are generally better usually end up having a better average score after these random games than the states which are worse. And so, if you were to choose the one with the highest random average score, then you would end up most likely choosing a pretty good move. Now, this technically isn't Monte Carlo tree search. This is a Monte Carlo evaluation at a single depth level. So you're not going further than this one depth. Now, let's pause here for just a moment. I would recommend that you learn a bit more about Monte Carlo tree search and how it works, and specifically applying it to a game called 2048. To do so, you can take a look at my course on cognitiveclass.ai. It's totally free, and it uses Swift for TensorFlow. There will be a link to that in the description below. If you like, you can only take a look at the 2048 module and come back to the video. Or if you like, you can take a look at the whole course that covers other reinforcement learning algorithms and AI algorithms as well. However, that will be very good base knowledge for you to build off of and understand the point of Monte Carlo tree search. So let's continue. Now from here, you've got to realize that we don't just want to take a look at one single depth. We want to go a little bit further down the tree and understand what the future holds for us. So what you have with Monte Carlo tree search is something called a policy. And a policy is something that will take your current state, and it's going to tell you, for my current state, I think out of all the possible moves, these are the ones that are the best. It's going to rank those possible actions from best to worst, and it's going to assign a confidence value to each one. So we're going to call these our policy values. So let's just say there are 4 possible next moves. So we have 1, 2, 3, and 4. And we're going to use a policy network to assign a policy to each one of these. All right, so we're going to assign a policy. Now what's going to happen is we're actually going to continue down this way. We're going to continue to expand the search tree for each of these nodes according to their policy value. Now, how do we determine which nodes to continue down with? Well, we're going to be using an algorithm called UCT, Upper Confidence Bound Applied to Trees. Now, I'm not going to get into how that works here. We'll talk about that more when we're actually taking a look at the code. But we're going to be applying an algorithm called UCT to determine which nodes we want to look at based off of their policy values, and then continue down the tree, so on and so forth. Now, let's just say we're going to a depth of 2, and in this case, we want to expand this one. Let's just say there's now only 2 possible moves, so we want to go down. Each one will have a policy, of course. But now we have, let's just say, reached our time budget, and we no longer have more time to continue down, so we're going to end the Monte Carlo tree search. Now you're wondering, how do we determine the value of these nodes so we know which action to take? Well, then something else comes in. We stop using our policy and we start using something called our value. Now, the value portion of Monte Carlo tree search is going to be able to take any state and just tell you how good that state is for you. So how good or how bad is this state for my current player? Now, it's a little bit different from policy. Policy is, for this certain state, what actions should I take? Value is, for this state, how sure am I that this is a good or a bad position for me? So what's going to happen is you're going to go to your leaf nodes and you're going to go ahead and calculate the values. So you're going to have a value 1, a value 2 here. This is going to have a value. Since this itself won't have a value, you're going to back propagate these values up through the tree. So this will have a value, this will have a value, and this will also have a value. And then whichever one of these nodes has the highest value, you're simply going to choose that one and you're going to continue. Now again, the way these values are back propagated up the tree, we're going to be taking a look at during our during the code as well. However, just know that this node's value is based off of its children values. And if these nodes had children, these ones' values would also be based off of their children's values. And finally, just like that, based off of the one with the highest value, you know which node or which action to take. Now, where exactly does AlphaGo provide its innovation? Well, you see, traditionally, how would we estimate these values? We would just simply devolve back to a Monte Carlo evaluation. We would run a bunch of random games. These are called rollouts, and these rollouts would help us determine what the value of a current state is. And the policy would be some kind of other set of heuristics that we would develop manually. Now, sure, this is an okay algorithm, and maybe GoBots like this can challenge human beginners, but once you get to human moderate or expert level, these bots pose absolutely no threat to any human player. And so, you've got to have a more intelligent way of doing this search. And so, what AlphaGo does is it uses neural network technology, deep learning technology to be specific. And what it's going to do is it's actually going to use those deep neural nets in order to guide and evaluate the search as it's happening. So there are two steps to making this happen: the policy network and the value network. The policy network is going to take your state and it's going to predict, using a softmax layer at the end, using a softmax activation, what are the best actions for me to take. Then based off of those best actions, Monte Carlo tree search is going to determine which nodes it should continue to search through. And then, here's the interesting part. When we reach a leaf node, we're not just going to run a random rollout, because first of all, that takes a lot of time. You've got to simulate games. It's simply impractical to keep doing that. And at the same time, they're random games. What can you really expect from them? So the value network is going to take that state and it's going to predict a single continuous value from -1 to 1, predicting how good the current board state is. What is the likelihood of the computer player winning from a current board state? And with those policy and value networks that contain almost no human knowledge, and I say almost, and you'll see why I said the word almost there in just a moment, but because they contain almost no human knowledge, because they're learning by themselves with deep reinforcement learning technology, they're able to play the game at a superhuman level. So we're taking classical techniques like Monte Carlo tree search, as well as these brand new techniques of policy networks and value networks in order to guide the search to tell us what moves are the best to make. That is the fundamental premise of the AlphaGo algorithm. Now, there are many evolutions of this algorithm, and there are many specifics that I didn't get into right now. For example, how do you know how much you want to explore versus exploit your predictions? Because let's just say there's a certain node with a very low confidence value, but that turns out to have higher confidence values for its children. Well, then maybe it's better to explore in the tree than it is to exploit your highest predictions. So during training, maybe you want to do that. But then at the same time, you don't really want to make a mistake just because you thought something with a low confidence could actually be pretty good for you. And so there are a few different issues that we'll take a look at how they're fixed during the code. But again, this is the fundamental premise. Now you're probably wondering, how are the policy and value networks trained? How do we get the data to actually get those neural networks to make these predictions? Well, AlphaGo has a lot of innovation in this front as well. What happens is the neural networks generate their own data. Now, I know that seems weird, but let me talk about how this works. So first of all, you've got your policy network, and you've also got your value network. What happens is, for AlphaGo in specific, not AlphaGo 0 and not AlphaZero, for AlphaGo in specific, what they would do is they would take moves made by professional human players over the past couple of years on online Go servers, and they would train the policy network to essentially predict what would a human expert do in this case. Now, these networks usually never reached great accuracy, only like 60-70% accuracy max, and that's after a lot of overfitting. But it doesn't really need to. Even with a low enough accuracy, Monte Carlo tree search will make up for the inaccuracy because it's going to be looking deeper in the actual game tree. So low accuracy didn't really matter. Then they used a similar technique in order to train the value network. They took 30 million Go games and sampled only a couple of moves from every single game. And then what they did is they took those boards and fed them into the neural network and had it predict -1 or 1 for lose or win for the black player. And what happened was the neural network was able to learn that, hey, these board states usually lead to a lose and these ones usually lead to a win. So it was able to generalize and understand what leads to a lose and what leads to a win in the game of Go. Now the thing is, just training on human professional moves isn't enough, because the neural networks don't really generalize to human moves. They very, very easily overfit since there isn't enough data, and that data is very variable. Different humans will make different decisions in different circumstances. And so there has to be a way for the neural network to get more data. Now think about this. If you were to play the game with only the policy network, so you literally just take the state, feed it into the policy network, get the maximum prediction value for an output, and just make that move, you wouldn't have a very good bot, because that bot can only see one move ahead into the future. Whereas with Monte Carlo tree search, when you're using the policy network in conjunction with this tree search, you're able to see further down the game tree and therefore make a better decision. So the policy network plus the Monte Carlo tree search makes better decisions than just the policy network. So what if you were to use the policy network in conjunction with Monte Carlo tree search to play games against itself over and over again? Well, technically, the data generated from those games would be better data than was just fed into the network. So you train the network again. Now you have a better network, but that network is even better when you put it with Monte Carlo tree search. So you generate even better data, and then you feed that data back into the network, and then you continue the cycle over and over and over again. And what happens is, after a few hundred or thousand iterations, you suddenly have a superhuman Go bot that plays Go at a level no human has ever seen before. And I just focused on the policy network for simplicity, but this also includes the value network. Remember, value network, great on its own, but it really shines when it's helping Monte Carlo tree search and not playing on its own. And so what you do is, with every single Monte Carlo tree search iteration, you have the agent play against itself, and you have it continuously generate better and better data to create better and better networks that will create better and better data. And by doing so, you have this infinite loop of progress that is very, very difficult to plateau. It just continues to grow and grow. And so that is the idea behind the AlphaGo algorithm. You have classical tree search, you've got neural networks working together to create a single superhuman system. Now, AlphaGo has two separate neural nets, policy and value. But later through the pipeline, when DeepMind evolved from just AlphaGo to now AlphaGo Zero and AlphaZero, they created a neural network that merged these two networks into one, essentially having a common head and two separate tails. So you would have a single feature extractor with a bunch of convolutional layers, and at the end there would be two separate outputs, one for the policy and one for the value. And so that's how these next neural networks worked. They were much better because the gradients for the value and the policy were able to work together to create a better neural network system and therefore guide Monte Carlo tree search better. But we don't stop there. There's one more thing I want to mention, and this is absolutely incredible. The inputs to these neural networks, the AlphaGo neural network, was of course the current board state, but it was represented in a pretty special way. So, for example, you could have a certain channel telling the neural network where all the black stones are, and then another channel telling it where all the white stones are, and then another channel telling it all the liberties of the black stones and the liberties of the white stones, and so on and so forth. And you would have manually human-crafted features in all these channels, and then you would feed it into the network. And when the network was trained, it started off with a bit of seed data from human experts, and then it took over from there and went into this sort of iterations of Monte Carlo tree search. Now, what if you could have a bot that just learned how to play Go by playing against itself and had no human data or expertise involved whatsoever? That's exactly what AlphaGo Zero accomplished. Now, they still did have some human-crafted features fed into the network. For example, the liberty counts, as I just said. However, these neural networks were not seeded with any human data. They started from scratch, and using Monte Carlo tree search plus the policy and value networks together, they learned how to play the game of Go. And here's the interesting part. AlphaGo was able to beat Lee Sedol, a human grandmaster at the Go game. And then AlphaGo Zero, which was trained on no human data, was able to beat AlphaGo 100 games to 0. That is absolutely incredible. But wait, it gets better. There's a new algorithm called AlphaZero, and AlphaZero not only starts off with absolutely no human expertise, but there are no human-crafted features fed into the network. So it's just given the raw board state. It's not given any manually created heuristics or features. It just has the current board, and it learns everything else on its own. And AlphaZero was then able to beat AlphaGo Zero. So we're starting to notice a bit of a trend here. The more human knowledge we take out of the system, and the more we allow it to just learn on its own, the better it ends up playing, because the more novel play strategies it's able to discover. Now, there is one more difference between AlphaGo, AlphaGo Zero, and the AlphaZero algorithm, and that is the arena. Now, what is that exactly? Well, let's just say you have a certain version of the neural network, and you use that with Monte Carlo tree search to generate some data. Then what would happen is you would train a new neural network, and you would have the old and the new play against each other. And only if the new network actually wins more than 55% of the games will you replace the old network and start to create new data. If it doesn't, for example, the training didn't happen very well, or the data for some reason wasn't good, then you discard the new network, you keep that data, you generate more data with the old network, and then you train a new one. And you continue like this until you create a better network to replace the old one with. But with AlphaZero, things are a bit different. You simply have continuous training. You don't have an arena stage, you have a single model that continues to generate data, train itself, and generate more data, and so on and so forth. Now here's the thing. Google is a rich company. They have lots and lots and lots of compute power to throw at this. They can throw 5,000 TPUs at just generating games like this, and they're barely breaking a sweat in terms of budget. And so they can spend a few months with 5,000 TPUs to continuously generate games and train a superhuman GoBot. But the thing is, the vast majority of us don't have that kind of compute power. And so we have to find other ways to train these networks. For example, there's a project known as AlphaZero, and AlphaZero is an open source implementation of AlphaGo Zero. So the naming's a bit off, but AlphaZero is an open source implementation of AlphaGo Zero. And this implementation is a distributed implementation. That means the average person, literally anybody, can download the AlphaZero source code, run it, and they are suddenly on their own computer calculating these self-play games that are then being contributed towards a larger model on the internet. And currently, one of the AlphaZero models is the strongest openly available Go playing entity that you can get. And so this sort of distributed effort is truly very powerful. But what I want to do today is show you an example that you can all train for yourselves. Something that you can just do on your computer and get an idea of how the AlphaZero algorithm works. And so today, we're going to be taking a look at how you can build a bot that uses AlphaGo-like concepts for the game of 2048. Now, 2048, in my opinion, is an absolutely fascinating game. It's only a 4x4 board, and there's only 11 possible values on each tile, so that makes it super easy to represent inside of memory and to actually implement the game itself. That's not a challenge. But the challenge is creating a bot that is smart enough to deal with the fact that the game is entirely stochastic. If you have a certain board state and you copy it 10 times, and you make the same move on each board state, there's a chance you'll get completely different board states. So it's fundamentally a stochastic game. And you somehow have to create an algorithm that can deal with that level of randomness. So 2048 is a fascinating challenge. I've already covered how you can use shallow Monte Carlo evaluations to play 2048 on my cognitiveclass.ai course, which is why I recommended you take a look at that. But today, we're going to be taking a look at how you can use Monte Carlo tree search, Monte Carlo evaluations, and the value network from AlphaGo in conjunction with each other in order to play 2048 better than any other non-human expertise bot on the internet. Now, there are some bots that people have already put together for 2048, and some of them are really popular. You're seeing one on screen right now. But the thing with these bots is that they are all based on human heuristics, and that is incredibly annoying to me. Because we have human strategies like, for example, taking a board and keeping the largest tile in the corner and then having the actual tiles go in descending order so that we can merge in sort of like a snake style. But the thing is, that's a fundamentally very human strategy. That's because we can't see far enough into the future to know how to maneuver pieces around so they merge and maneuver in the right way. But computers can, so why don't we leverage that ability of theirs? And with the power of this AlphaGo algorithm and with the power of Monte Carlo tree search, that's exactly what we can do. The bot that I'm about to show you when we go over to the code is a bot that plays with absolutely no human knowledge involved whatsoever. And because it's using no human knowledge, it plays in a very weird way. It just looks alien whenever you look at it. If you're a professional 2048 player and you take a look at this, you're gonna think it's making the dumbest moves it could make. But when you actually take a look at more than just a single move, when you take a look at an entire episode, it's mesmerizing how this 2048 bot can take a state that looks like it's just about to lose and turn it into a 2048 tile. It's really fascinating stuff, and I don't think I can just explain it. I don't think words will do it justice here, so I think it's better for you to take a look at a demo of the 2048 bot in action, and then we'll get into how you can actually build a value network for 2048 and how you can leverage it with Monte Carlo tree search in the Swift language using Swift or TensorFlow in order to build your own 2048 bot. Let's take a look. All right, so now let's take a look at how this AlphaGo-inspired 2048 bot actually works. Now, before I actually show you the code behind it, I think it would be really fascinating to take a look at the actual demo running live. So what I'm going to do is I'm actually going to run the backend code here in Xcode. So I'm running this code from within Xcode. This is written in Swift. And what it's going to do is it's going to open up a Ketura server on port 8080, which opens up just one simple REST endpoint that takes the current 2048 board and spits out the best move to make. Now, if we switch back over to my web browser, you can take a look at our 2048 game. The 2048 game is also being hosted by Ketura, and I've modified this from Gabriel's implementation just a little bit. So there's just two extra functions that will enable auto movement, where you just click a button, and every single move, it will take the board, send it over to my REST API, figure out the best move from my little AI, and then brings it back over to the interface where it actually makes that move and continues until the game is over. Over could mean that it's lost or it's won. So watch this. Right as I click the T button, just like that, it goes on its way. Now, what I want you to realize is that, first of all, I mean, as I mentioned already, we're taking this board state, we're sending it over Swift, it's coming back, but it's doing so incredibly fast. You wouldn't think that a 2048 AI could be this performant. Now, there are some more performant 2048 AIs out there. In fact, the only other one that's faster than this is one that I've also built, and that's the one that you would have seen on cognitiveclass.ai. However, what's interesting about this is that it's not just doing a single depth Monte Carlo evaluation. It's doing both Monte Carlo evaluations and neural network predictions, and it's still this fast. That's how fast the Swift language can be if you write your code the right way. We'll talk about that in a moment. Now, I want you to notice something about this play style. I told you it was unorthodox, but now that you're looking at it, you're probably really starting to realize just how weird it is. Humans have this strategy of keeping similar tiles closer together so that you can merge them more easily. So for example, in this case, you would probably have 512 in a corner, and then 256, and then 128, and so on and so forth, so you could easily merge into and get to the 1024 tile. But this AI didn't need to do that. It just had them in completely random places, and out of nowhere, it sort of emerged that it had created a local path of merging where it merged 128 and 128 into 256, two 256s together, and then those into a 512, and then two of the 512s together into a 1024. And you couldn't even see that little local aisle that it created for that merging, but it did. And we'll take a look at some slow motion footage of this in just a moment towards the end of the code section, but I just wanted you to get a feel of just how weird the code, just how weird the actual gameplay is. I mean, if you take a look at the most popular 2048 AI out there, and if you take a look at that YouTube video, all the comments are about how sometimes the AI ends up moving the highest value tile out of the corner because it's very human strategy based. But this one, it's not following any human strategy. So it's making really what seemed to us as bad moves. I mean, if you were to just pause the game in one instant, you might think there's no way you're going to win this. But then, as you can see, it goes ahead and wins the game like that. So this is really fascinating stuff. So now let's head back over to the code and start to take a look at how this actually works. I'm going to go ahead and stop the app so we stop taking up memory and CPU so we can actually focus on the code. Now, what you're seeing over here is all the code that goes behind the actual sort of quote-unquote intelligence portion of the application. Now, there are some other components to the app. For example, there's the actual 2048 game logic. Now, here's the thing. The 2048 game logic is pretty intense. And the reason for that is because 2048 is a little bit more computationally complex than you may imagine. So if we go back to the 2048 game, and if you've already seen the cognitive class course, you may already know a little bit of this, but just in case you haven't, I'm going to quickly walk you through it. If you've got, for example, a board like this one, you can see there's only 4 rows. Now, each row has a tile, and the tile only needs to store a value from 0 to 11. Now, technically, the values actually range from 0 to 2048, but we're storing them as powers of 2. And so you can just store 0 to 11 because 2 to the power 11 would be 2048. And so what we need to do here is we need to somehow have a super fast implementation of the 2048 board. So that, for example, when I click the left arrow, we don't need to compute all the tile merges and how everything needs to move to the left. Instead, the way this algorithm works is it actually pre-computes before the game starts every possible row, of which there are around 65,000 possibilities. And then for every single possible row, it pre-computes all the merges in all directions. And then when you click the left arrow key, all it's doing is it's taking each row, it's looking that up in the table, and it's saying, all right, for this row, if someone clicks left, what do I need to change the row to? And it's picking that up and assuming that's the new row. If you click up or down, then it just transposes it, so rows become columns, and columns become rows, and then it does the same thing and then transposes it back. And so that's how this works, because it needs to be really, really fast if we want it to be this performant. That's why my other AI, which has a lower winning rate than this one because it's only based off of Monte Carlo evaluations, that's why it's the fastest out there, is because it's so rigorously optimized like this. And this implementation also benefits from that because it builds off of that implementation. So if we go back, as you can tell, there's quite a bit of code that actually goes behind determining these values. So if we continue to go down, you can take a look at all this implementation code. It ends up to be approximately 464 lines of code, but then again, that's with all sorts of spacing and comments and other utilities. So you could definitely minimize this, but it is quite a bit of logic, but it's absolutely worth it. And finally, we can get to the actual intelligence portion of the application. Now, the way this works is from a coding perspective, as you'll see, super elegant. It's not to say that it's simple, but rather that the pieces feel natural and they feel like they should fit together. And that's what's so amazing about the AlphaGo series of algorithms, is that they're not incredibly technologically complex. It's something that people can understand if you do enough research into it. And this is the first application ever of those techniques to the 2048 game. So let's take a look at how that works. Now, of course, in the beginning, there's just a couple of imports. In Swift, we're only doing a few key imports: Foundation, TensorFlow, Python, Kit, and Ketura. Foundation, of course, default Apple stuff, going to give us some good Swift utilities to use. TensorFlow, the Swift for TensorFlow framework, is going to allow us to create some deep neural network architectures within the Swift language. Python Kit will actually allow us to load Python Keras model weights into Python. Into Swift. And so what I'm going to do is I'm going to import Keras, and then using Keras, I'm going to load a model that's saved on my disk, and then I'm going to use Keras to export those weights to a NumPy array, and then import those NumPy arrays into tensors in Swift that I'll put into my model. And then finally, there's Ketura for actually opening up that REST endpoint that the 2048 game can access and find the best moves for. So those are the key components that go behind this entire application. Then, of course, we've just got our standard imports. We're importing NumPy and models from TensorFlow.Keras. And then I'm using that module to load a model just called model.h5 in my home directory, user/Tanmay. After that, there's a little sort of utility function that I put together called tile processor. The tile processor takes a two-dimensional array of rows. A row, if we actually look up its definition with Xcode, is just a 16-bit unsigned integer. And so again, we're using a bit board, super optimized implementation of the 2048 board. And what that means is each row is 16 bits. And so that means that we have 4 individual tiles in each row, and each tile only needs 4 bits in order to be represented. And so 16 bits. Because again, we only need those 4 bits to store up to 11. So now if we go back, we can take a look at the tile processor function again. It's taking that 2D array of 16-bit unsigned integers, and it returns a floating point tensor. The shape of this tensor is 1, 4, 4, 11. So what that means is we have one sample and each sample is 4 by 4 by 11 large. 4 by 4 meaning the actual board, and 11 meaning the channels that we're feeding into the actual algorithm. So how does that work? Well, basically what we're doing is we're not just going to feed in the raw board to the neural net, because that doesn't perform particularly well. Rather, what we're going to do is create a brand new array with 11 channels. And in each channel, we're going to assign each channel to a certain kind of tile, and every value within every channel will be 0, except if a certain location on the board contains that kind of tile, then it'll be a 1. So for example, within the very first channel, all the positions within the board will be 1 if that tile contains a 2 value. In the very last channel, the positions within that channel will be 1 only if the board contains a 2048 at that position. And within you get the values between 2 and 2048. And this is a much better representation of the 2048 board for the model to work off of. And so this logic is essentially just responsible for that. This is going to find the actual log base 2 of the actual value. So for example, if it were 2048, what it would do would be the simple logic of get the log of 2048 and divide it by the log of 2. And then you would get 11, which is our maximum value here. And then finally, you would just go ahead and feed that into the tensor. So that's how that would work, and then you would just reshape it and return it from the function. So again, relatively simple logic. Now, from there, we continue and we can take a look at the actual logic behind the model itself. Now, the thing is, if you've ever used Swift for TensorFlow, you know that there's a layer protocol, and most models are supposed to conform to the layer protocol. But in this case, I did not have my model conform to that protocol because I didn't need to. Because usually you would use the layer if you were actually training the model, or if you were calculating gradients or something of that sort, or if you were using it with other layers. But in this case, I don't actually need to do any differentiation. I don't need to do any training. I'm just loading in a pre-trained model from Keras, and I'll talk about that in a moment, how I actually trained it. So I'm only conforming to the key path iterable protocol, and what that lets me do is it lets me take all the stored properties within this actual structure, and it allows me to recursively iterate in this entire structure and all of its stored properties and all of their stored properties and so on and so forth, and find the key paths within the structure to every floating point tensor. So what that's going to let me do is find the tensors, find the variables that contain all the weights for all the different layers within the model. And that's going to let me load in my weights from Python. So that's why we're doing that. And the way I'm going to do that is by calling a function that's defined within this protocol called recursively all writable key paths. So I'm saying recursively find all of the key paths that I can write to, as long as the key path is to a floating point tensor. And then I'm looping through that, and for each weight, I'm finding the respective Python weight and loading that into Swift. So that's how that works. And the way this structure works is I'm implementing a singleton model. So I'm not going to create an instance of this structure anywhere. Just within it, I have a static constant with this model defined already. And the initializer is private, so you cannot create more instances in other places in the code. You've got to use this shared instance. So that's how this works. I'll also talk about this model and why I chose the actual filters and layers that I did in just a moment. So moving on from here, I'm also just defining a simple constant array that's telling me the order in which I like to define my directions. So the way I'm defining that is just up, down, left, right. So whenever I give you an index for a direction, like let's just say I gave you the index 2, that means I'm referring to 0, 1, 2 in this array, which is left. So this is just so that I have a standard integer representation and index representation for every direction. From there, I'm just defining an epsilon, super small value, to make sure that some values aren't 0, just 1e minus 4. You don't need to worry about this value, it's just we need this in Swift, and we need this for Monte Carlo tree search. Specifically for the UCT algorithm that we'll implement later. Then I've just got a few utilities over here in my code. These utilities are pretty standard if you're coming from a Python world, but unfortunately they need to be defined manually in Swift. So for example, within the collection protocol, I'm extending that wherever the element is comparable, and I gotta say, the Swift generics make this super easy. So every single collection type, this includes arrays and sets and dictionaries or whatever, wherever the element is a comparable element, I'm adding functionality to that collection called argmax. So the maximum argument, it'll give me the index of the largest element within that array. And it's optional technically because if the collection is empty, you're going to get a nil result. So that's how argmax works. And then just a couple of array multiplication and division functions, custom operators or custom operator implementations that are pretty generic and work across multiple types. Then we've got the actual meat of the algorithm. So then I've got a function called Scoreboard. Now, Scoreboard is going to take a board, and this board isn't like an array representation of a board. This is a bit board, so it's just an unsigned 64-bit integer. So again, if we take a look at the row, each row is 16 bits, and we've got 4 rows. 16 times 4 is 64. So it's pretty convenient that we have a 64-bit unsigned integer that we can store our boards in. And the way that I actually score boards is super simple. Just take the model, the shared instance of it, feed the board into the model, and then rescale it from -1 to 1 to 0 to 1. This is used for Monte Carlo tree search. Again, we will be getting into Monte Carlo tree search in a later video, but what I will tell you is the way we do this is we simply add 1 to the prediction and divide that by 2. Rescales from -1 to 1 to 0 to 1. And then finally, there's the Monte Carlo search. Not tree search, the Monte Carlo search. Now, the way this entire 2048 bot works is it's kind of weird in a way, in the sense that it's not entirely AlphaGo-like in the fact that the policy and value heads are neural networks, but it's also not entirely primitive. It sits somewhere in between. The policy is calculated by a Monte Carlo evaluator, but the value is calculated by a neural network. Because the thing is, neural networks aren't particularly good at comprehending 2048 boards because of their stochastic nature, and because of the fact that 2 moves don't really make all that much of a difference in whether or not you lose a game. Right now, if you had some sort of 2048 board, I could make 3 random moves, and you probably still wouldn't lose the game. There's a way you could maneuver the board in order to fix those mistakes. At least that's how this works. And neural networks cannot model that policy very well. And so that's why the policy is being calculated by a Monte Carlo evaluator, but the value is being calculated by a neural network, because the value neural networks are pretty good at understanding. Are you close to losing the game or not? In fact, I was able to get around a 0.02 mean squared error loss on a validation data set that I had for training the network, and I'll get into that in just a moment. This Monte Carlo search, if you've seen the cognitiveclass.ai course, it's really familiar to you, so I'm not going to go over it in much detail. Just know that it takes a game state as an input, and then it returns just an array of floats, and this array is always going to be 4 elements long no matter what, each index referring to a direction, and it's going to give you a probability for each direction that they all sum to 1. So it's going to give you the directions that it thinks would be best to move in, essentially. So again, pretty much what the output of a policy network would be in the actual AlphaGo algorithm. Now from there, we start to get into the fun part of the intelligence, which is the search and score. The search and score actually takes a board and returns 2 outputs, the policy and the value. So what it's going to do is it's going to run the evaluator that I just showed you for the policy, as well as the value network to score the board. And it'll return both the policy and the value, and this is what enables the Monte Carlo tree search to be this intelligent and know where to look exactly. And then finally, you've got the Monte Carlo tree search. Now, as you can tell, Monte Carlo tree search is a pretty hefty algorithm here. And the entire purpose and the way Monte Carlo tree search works is a topic for a separate video where I'm going to show you how you can actually train your own AlphaGo, including the policy network from scratch. That's part 2. However, for now, I will tell you how one of the 2 functions works within the structure for Monte Carlo tree search. And that is the get action probabilities. Now, within get action probabilities, this is the main function that you're hitting within Monte Carlo tree search, or MCTS as I'll call it from here on out. You're feeding it a board and a temperature. Now, what's a temperature? Well, the temperature is going to tell your model how open you are to new ideas or exploration. So if you've got a really high temperature, things are moving around a lot, then, maybe you want to have a little bit less of a very peak in terms of prediction probabilities, predicted probabilities. Maybe you want to have a more smooth probability matrix. In that you're okay with exploring other options that aren't necessarily as good. But then if you've got a really cold temperature, a really low temperature like 0, then you only want to have a 1 for the top prediction and 0s for everything else, so that there's no chance of you looking in the wrong direction. Or at least according to the Monte Carlo tree search. So the way this works, the way this function actually executes, is it runs a number of Monte Carlo simulations. So it's actually going to find a node, it's going to expand the node, it's going to run its value network, it's going to back propagate those values up the tree, and it runs a number of these simulations, and that's defined within the actual structure itself. And then what it does is it actually takes it's able to calculate the probabilities for visiting each, for choosing an action. And the way it calculates those probabilities is by actually taking the visit count of each node. Again, you don't need to understand what visit count means just yet, that's for the next video. But what it does is it takes the visit count for each node at that root level, and if the temperature is 0, it just gives a 1 for probability wherever the node the action has the highest visit count and returns that. Otherwise, it's going to actually go ahead and calculate that probabilities according to that temperature and then return that array. So essentially what it's doing is it's calculating probabilities based off of visit count, and that visit count is determined by the actual searches that the Monte Carlo tree search does. Now, traditionally, the more searches you do, the more simulations you do, the better your result is going to be. But then again, that also means your result's going to come to you slower. Now, because we're actually running Monte Carlo evaluations and not using a neural network for the policy network or the policy algorithm is pretty compute intensive. And so we always want to run lower simulation counts, otherwise it's going to be super slow. But if we were to transition to using a neural network, then we have the ability to use more and more simulations, which allows us to look deeper within the game tree. And so that's why AlphaGo uses neural networks, because you don't need to have to think about what the policy is going to be. The neural network just has that knowledge and you're able to leverage that. And so the actual search algorithm, I cannot do it justice in this video. We're going to be talking about it later. On a very high level, what it's doing is it's doing a few key steps around choosing nodes, expanding those nodes, and back propagating those values up through the tree with this logic over here. And then based off of the visit count that's calculated over here, we can go ahead and determine what the best action to take is. So that's Monte Carlo tree search in a nutshell. Now from here, we've got our Ketura code. So the intelligence is over, and I know it's like, wait, what, that's it? Well, remember, we haven't covered training yet. We haven't covered quite a few things. So let's take a look at this Ketura code. This Ketura code is just going to open up a static file server, and that's just going to say, okay, whatever's in the public directory, just open that up on the root endpoint. So this would be the 2048 game, since it's built in HTML and JavaScript. And then finally, I'm going to open up a new Monte Carlo tree search instance. I'm going to run only 6 simulations. Again, you probably want to run as many of these as possible, but 6 is a good balance between very high win rate and at the same time very good performance. And then just open up an endpoint called analyze, take a board from the JavaScript code, go ahead and predict using Monte Carlo tree search with a temperature of 0 so we don't make any mistakes. Go ahead and choose the argmax from that, so get the action with the highest probability, and then convert that direction to a string and return that from the Ketura code, and then continue from there. And so that is essentially how this entire intelligence code works. Now, how did I train the value network, you may ask? Well, here's what I did. I set up this thing called a thread pool. Now, this is very generic code. This is in no way specific to this application. Like, you could copy and paste this code that I've written into any application. You could use the thread pool that I've written. And this thread pool is relatively simple. Basically, what it does is it takes a function, so a closure, and it stores that closure within the structure. And what it enables you to do is specify, all right, I want to run this function on this array of inputs, and I want to get an array of outputs, and these can be totally generic types. The inputs and outputs can be anything. And I only want to use a certain number of threads, though. So let's just say you had a task like Monte Carlo evaluation. Now, if you only had 16 threads on your computer and you had 30,000 boards to analyze, and if you were to just do a loop for I in 1 to 30,000, and if you were to do dispatch queue.global.async on every one, you would be launching up 30,000 threads. Well, not actually, because the scheduler is a bit more intelligent than just letting you spawn 30,000 threads. But you've overloaded the system. You've given it too much work to do, and there's so much context switching happening that it's not really doing a good job at any of them, and so it ends up being pretty slow. But this thread pool makes sure that you're only running n number of things at once, so threads number of thing at once. And then every time something is done, it launches a new thread and opens up and tells it to do some work as well. And the way this works is it uses 3 semaphores to make sure, locks are making sure that the code is thread safe, and it returns its outputs in a synchronous fashion. So when you call this function, it'll block until all your work is done, and then it returns the output to you. So that's how the operate and the thread pool works. So with this thread pool, what I did is I actually completely let go of Monte Carlo tree search, and I just took the Monte Carlo evaluation. So what I built in my cognitive class.ai course, the world's fastest 2048 AI. And with that, what I was able to do was actually build a data set of 3,000 2048 games, which had a win rate of approximately 65%, which is not that great, but it's also not bad either, considering that of all the games played on 2048, only about 1 or 2% were actually won by humans. So a 65% win rate definitely isn't bad. And with this data set, I exported that to a NumPy array, put that onto a GPU server of mine, and used a Python script in order to train a model to predict, based off of the current board state, what's the likelihood of me actually winning this current game. Now, there is a bit of a problem with that, though, and that is that the 2048 game is complex. From the very, very beginning, from the very first few moves, there's very little you can do in terms of understanding the initial board and determining if you're going to win or lose. Because even if you were to do random key smash for the first 100 moves, it doesn't really matter, because the first few moves are so rudimentary anyway that you can recover from there and win from the worst board state. However, the neural network model doesn't understand that. What's going to happen is it's going to have 3,000 inputs where where 65% of them are wins and the rest are all losing board states. And it's going to take those initial board states and try and overfit to specific board states, telling it that, hey, this is a win or this is a lose. So the way I solve that problem is actually pretty interesting. What I do is I run the np.linspace function, so I generate a linear space. So let's just say a certain game was 900 moves long. What I would do is generate an array with 900 elements going from 0 to 1, assuming that we won the game, that the model was able to win the game. We go from 0 to 1. Now, here's the thing. We're incrementing with just a linear increment every single time for every element in the array to get to a 1. But then what I do is I take every element and I actually replace it with that element to the power of 9. So what that does is it gives me a bit of an exponent. It gives me a curve that says moves made towards the end of the game are more likely to actually have affected the end result of the game. Whereas towards the beginning, your predictions can be closer to 0 because you're not really sure which way the game is going to go. And if you go ahead and actually plot out the value throughout the game, you're going to see the value network actually follows that curve. Towards the end of the game, it starts to make stronger and stronger predictions, and they start to get better and better. In the beginning, they're not very good. It keeps jittering up and down, but that doesn't matter because I trained it to make sure the values are close to 0 at the beginning, and only towards the end of the game will it actually start to make more confident predictions. Now, if the model had lost the game, then we would do the same thing in reverse. We would do 0 to -1, and then technically still 0 to 1, and then every value to the power of 9, and then multiply those values by -1. And so we would be able to take that and create a curve in the opposite direction. And by doing that, the model was able to learn a really good representation of what makes a good 2048 board at what stage of the game. This isn't something that DeepMind did for AlphaGo, but it's something that I did as a game-specific optimization for 2048. So it just goes to show how you can take research done on a completely different kind of game with a completely different kind of playstyle and apply similar research to play, again, a completely different kind of game, but using the same fundamental techniques. Now, the actual code for training this value network will be available as a separate repository to this code on GitHub. Both GitHub links will be in the description for you to see and for you to use. I will also have a little bit of Swift code in the initial repository of how you can actually generate that data set. And so that's how the training actually works. And with that, you're able to create a really fast, a performant, and a model that reaches an over 85% win rate on 2048. And that's with only 6 simulations. Imagine if you were to do more simulations, which you can quite easily do just by tinkering around with this one individual value over here in this initializer, you could get much higher win rates by allowing the network, or by allowing the game tree to be expanded further and further down. Now, once again, you simply run this, it opens up an endpoint, and you're free to experiment and go ahead and run your very own 2048 AI like that. Now, there is one more thing that I want to show you before we end off today, and that is this over here. Now, as I mentioned, some of these moves are kind of magical. The way it just happens to plan everything beforehand in this stochastic environment, and how it just makes things work, and how it creates these local aisles of tiles to merge. So here's what's going to happen. This is the ending stage of one of the 2048 games that uses this exact technique that I just recorded because it's so fast. And I'm going to step through this frame by frame to show you just how fast and how genius the solution was for this game. So take a look at this board. Now, this isn't, from a human perspective, this isn't a great board. Now, you have all the pieces necessary to get to 2048, but they're not merged, and they're not in a good position to be merged. But look at this. If you take a look at this column over here, there's only one space at the top. If you hit the up arrow key, you're guaranteed to move these 3 tiles up, and that means these 232s are going to be aligned. But what does that also mean? That also means that after you merge them to the left, there's a 64 beside it to merge into a 128. And then we're going to continue from there and merge everything else back into 2048. Let's watch. So we step ahead frame by frame. The network had just made a move, and so it actually spawned a tile in the top right corner. I move ahead a few frames. Oh, as you can see, it merged down here, and it spawned a tile there, the 2. It's going to go ahead and move left. So again, this is fascinating stuff. It moves left. It goes ahead and moves up. So as I was saying, now we've got the 232s aligned. It's going to go ahead and move back down to keep the 32s aligned, and so the 64 is on the right so we can merge that in eventually. Now, look at this. It'll merge the 232s, and now it's got a 64 there. All right, now I know it looks a little bit choppy, but I'm actually going through frame by frame because it's so fast I have to go through frame by frame. Now watch, it's going to merge the 264s, and it had already envisioned this situation, and the other 128 tile is already above this 128 tile. So I go ahead, it goes ahead and clicks down, the down arrow, and suddenly it's got a 256, and how convenient. It's got a 256 right beside that tile waiting for it. So it goes ahead and clicks down to prepare or something. Again, these are moves that I can't entirely explain because I'm not the algorithm, but it goes ahead and makes some moves. Now it goes to the right to actually merge the 256 tiles, and pause for just a moment. Notice how this algorithm is not greedy at all. It's unlike a lot of other algorithms in that it's not looking for short-term gain. It's not just trying to say, okay, how can I get the most merges right away? It was like, even though I've got 256s right there and I could make a 2048 pretty quickly, I'm not going to because I'm going to maximize my chances by making this other move. Because that's not going to affect my current board state with these local merges, but it might be beneficial in the future. And so the way it thinks is pretty fascinating. Now you've simply got 512, 512, and 1024. You've got to merge them to make the 2048. How does it do that? Well, we may never know exactly how it came to that move because it was so fast that within a single frame, it was watch, I'm just going to click the right arrow. It's going to move the video ahead by a single frame. This was recorded at 60 frames per second. It somehow merged those two into 1024s, and in the very next few frames, the two 1024s become a 2048 tile. And just like that, the network has won the game. And so that is absolutely fascinating, the way this technique works. And if you find something interesting that you see the model is done and you end up recording it, please do share that with me. I would absolutely love to analyze more results, get a better understanding of just how this technique is playing 2048, and what's really going behind it. And so if you enjoyed this tutorial, please do make sure to leave a comment down below. If you have any questions, suggestions, or feedback, you can reach out to me on all sorts of social media, my Twitter, or my email, which will be in the description below. Again, all the code and the links, for example, the logic behind Monte Carlo tree search, that will be in the description below for you to check out. Apart from that, if you do want to see more content like this and you do enjoy these videos, please do make sure to subscribe to the channel, as it really does help out a lot. And once again, thank you very much for watching. Goodbye.